Welcome back. So, last time we spoke, we managed to get Vieti's pi algorithm working with the decimal data type with a small caveat. The final two digits are wrong. I am not entirely sure if this has to do with the problems that computers often have with, like, dealing with decimal numbers, or a problem in the algorithm itself. And I gave it some thought. I think we're going to try another pi algorithm. See if we get different results. And the algorithm for today is the Gregory-Leibniz series. Pi equals 4 over 1 minus 4 over 3 plus 4 over 5 minus 4 over 7. Basically, you swap the from positive to negative on each iteration, and you start from 1 and add 2 on each iteration for the denominator. And basically you keep going until you get, like, theoretically, you can get as close to pi as you want. It says it converges quite slowly. It takes 500,000 terms to get 5 correct decimal places, which is a lot compared to the one we've been using, Vieti's pi. Here, let's see the number of iterations we need to solve here. Just to get an idea of how many iterations we need for Vieti's pi to fill out, like 47 iterations. It's gone as far as it can, for better or worse. I'm gonna write that down. $47 to fill, to max out the decimal data type. And we're going to make a new pi function. What should I call it? Gregory's pi, Leibniz's pi. I'd hate to leave one of them out. They both worked on it, whether together or separately. We'll call it the Gregory-Leibniz pi. Actually, we don't need to inject the square root function because this one doesn't actually require a square root, which is cool. So pi equals 4 over 1 minus 4 over 3. We're going to need our big while loop again. Working with the decimal data type, the sign begins as positive, plus 1m. On each iteration, we invert the sign, and then numerator is always 4. Denominator starts as 1. And then on each iteration we invert the sign and we add 2 to the denominator. Pi starts out with a value of 0, and then on each iteration we do pi equals pi plus the numerator divided by the denominator. But we actually want to do it like this. Oh. Because we're going to store the value of pi on this iteration, and then if pi 0 equals pi, return pi 0, because that is the final pi. And now, we're going to see if Gregory-Leibniz can give us a nice big fat slice of pie. Gregory-Leibniz's pie. And I want all my columns lined up. Alright, let's see what we get. It's a pretty simple algorithm. And it is running. Huh. Let's see. 500,000 terms to get 5 correct decimal digits of pi. That's rough. Okay, let's see if we can get some sort of reporting going on. Alright, so we're going to print out the iteration number and the current value of pi. And let's let it rip. That's not even close, because I'm not taking the sign into account. That'll help. You gotta flip-flop that sign on each iteration. Alright, try again. That's looking pie-shaped. But as stated in the Wikipedia article, it is a slow convergence. Now, something that Gregory-Leibniz's pi has going for us that Vieti's pi did not. Vieti's pi relies on the previous value of pi to calculate the next element in the series. But in this case, with Gregory-Leibniz, each element of the series is roughly independent. And you just gotta, they all just have to eventually sum up into the full pi. So we're gonna let this run for a while. A long while. And we're gonna see if we can we're going to see if we can run this in parallel. To do that, right now the value of sine depends on the previous value of sine. And that's not going to do. Pull this down here, and let's see, if the value of iters is odd, it should be positive. If it's even, it should be negative. So there we go. It says if it's even, then the modulus is equal to 0. Modulus of 2 is equal to 0. Then we want the sign to be positive, otherwise we want the sign to be negative. We don't need to recalculate the sign. And then the denominator, that's currently dependent on the previous value of the denominator. Let's bring that down. The denominator is equal to, it's like 2 times the iteration minus 1, I think. So when the iteration is 1, problem is we need this to start as a 0. So the first iteration is iteration 0. Iteration is basically even, so it starts off with a positive sign. That's correct. The denominator should be 2 times 0 minus 1, which is 0. Well, 2 times 0 is 0 minus 1, so the first value of the denominator is negative 1, which is wrong. If we do a plus here, then 2 times 0 plus 1 is 1, which is correct, and the next on the next iteration, iters is 1, 2 times 1 is 2, plus 1 is 3, so we go from 1 to 3, and then when iters is 2, we got 2 times 2 is 4, plus 1 is 5, so this is counting up odd numbers. Let's see, how many digits are we at? 1, 2, 3, 4, 5, 6, 7, almost 8 digits of pi. And we are in the, let's break this, stop it, 23 billion iterations. It really does converge slowly. Alright, so the way we can do this I wonder how many iterations we would need to fill out the entire width of what a decimal value can hold. Parallel for from 0 to, let's see, 23 million wasn't enough. Let's say, okay, we're going to start with 500,000. And then we need our action. Except I need this to return a series. Basically, I want to run a bunch of iterations of this algorithm simultaneously, and when that's all done, we'll add all the segments together. And this returns a result, but what's in the result? Just whether or not it completed. Oh, that's not what I want. Maybe that's the wrong type of thing. So let's say we have an enumerable. Range 0 to 500,000. And for each of those, we can run a function. Now the problem is, I want to select all of them simultaneously. Now we could like throw all the values into a concurrent stack. And at the end, sum them all up. Just don't take one argument because that has a cancellation token. It's now an async function. Not all code past return a value. What's a value task? I don't know what a value task is. Provides an awaitable result of an asynchronous operation. Just gonna do normal for because the individual actions are not awaitable, and I think that's what's gumming up the works there. Now, an awaitable function, or async function, needs to return a task. And we cannot do this fun thing where we're doing an early break from the loop because, I mean, we might be able to take advantage of that cancellation token. Oh, why is it upset now? It's just not awaitable. It's been a while since I've actually used a parallel for. Console output is not going to be very useful because it's just going to give us one of the little segments of the series, which isn't going to mean much. Not by itself, anyway. So, just going to return a decimal. Not doing anything with the result yet. I don't know if we will. We have pi 0. We need to actually add that to our values stack. Okay. That should nicely heat up my CPU, calculating 500,000 iterations of this infinite series simultaneously. I'm so curious. Alright, let's see what this does. Oh, it just returned almost immediately. Well, that's nice. And it gave us the first 1, 2, 3, 4, 5 digits of pi. Of course, we're wanting all of the digits of pi. We are greedy. We want to get all of an infinite series. So instead of 500,000, we're going to try 5 million. I'm waiting to see if my CPU starts spiking. But no, it just returns almost immediately again. Okay, you like 5 million? Let's try 50 million. It's thinking a little bit. CPU graph is heating up a little bit. I'm feeling somewhat more satisfied that I'm giving my CPU some exercise. It's like I have 16 CPUs. They should be doing some work. Alright, so that got us all the way out here. We need those. I want those last 5 digits, and I want them to be correct. How many iterations do I need? That is, was it 50 million? Let's try 100 million. I think I can do this. Okay, yeah, I can do that. 100 million, let's go. Come on, Gregory-Leibniz, do not let me down. And the CPU is getting interested. Now, ideally, you would calculate this once and then store it somewhere. It's neat because you can actually see the CPU cycling down just before the program exits. 100 million was not enough for those last 4 digits. So, we're going out to 1 billion. Will 1 billion give us the digit count that I'm wanting? Here goes the CPUs. Watching all those numbers crank up. Go little CPUs. You're not 100% yet. You could work harder. Do it. Give me a big slice of pie. Go, CPU, go. It's really trying. I appreciate that. I wonder if there's some way that we can get it to use more of the CPU, though, because it's like each of the CPUs is only, they're not breaking into the 70% range. I don't know if this is a limit that Ubuntu is putting on the .NET virtual machine, or if it's something built into the way the parallel for loop works. So we're just going to keep waiting for a minute. Now you could fast forward the video at this point to get to the answer, But it's so much more exciting to wait in anticipation of, like, how long is it going to take? I'm so excited to see if this is going to give me all the pie that decimal number can fill. Something just spiked. It's probably unrelated because the network spiked at the same time, and nothing in this program is related to network usage. Oh, it's slowing down. We're almost there. And the final result is close, but we're not there yet. Oh, it's so close. There's a couple of ways we can handle this. We can set the upper end of the range to the maximum value of an integer. We can have it add into the final value of pi using yet another background task that will lock pi, add the number, then unlock it, and then trigger a cancellation token when it's actually done. Or we can just like add another 0, and that's valid too. I wonder if there's anything else we can do to make this run more efficiently. The most time-consuming part of this process is probably going to be pushing the final value onto the concurrent stack. Just wondering if there's anything else here. Parallel options. Okay, there's this parallel options construct. Let's see what it gives us. Cancellation token, max degree of parallelism. How far can I take this? Oh, this might be a bad idea, but it's okay. And this will take a task scheduler. Can't create it. It's an abstract class. You can grab the current or the default. No, I don't think it's worth trying to overwrite that one. But we can set the options. Just telling it that you can run as far parallel as you can possibly imagine. I wonder if this is going to break the recording software. If the video cuts out here, then we'll know why. is there another way that we can report on the output? I don't know that there is. It's like the numeral have, like, you can do a select, but it's not asynchronous. So we don't necessarily need to push onto a concurrent stack, we just needed to return all the values. I don't know that there's a difference. Okay. We're going to run this again. 10 billion iterations. Explicitly setting all these to the same data type just in case it matters. Can I do this? No. Okay. Okay. Try again. This is going to take some time. And we're off. Whoop! Arithmetic operation resulted in an overflow. Line 34. I wonder if it didn't like what I set for the options. It might not have. Could be that the only way to really run this is to just let it run. And we're going to just let this run for a bit. I'm not going to hold you here for the end result. Although we are breaking into the 70% range, so it's like, I feel like the CPU is really giving it a try this time. It's going to get closer. I don't know if it'll get close enough, but that's as far as is probably worth taking with Gregory-Leibniz for today. There are other algorithms that converge faster. I don't know if they can be run in parallel. Running it in parallel is not gaining us as much as I would have wished. V80's algorithm, you can't run it in parallel, but you also don't need to because you only need a couple dozen iterations. Aside from the whole getting the last couple of digits wrong, which I can't explain yet. If I study it long enough, I'll figure it out. What I want to try next time is rendering the value of pi in a different base. I'm going to explain the problem while this program works itself out, but let's load up another terminal. It's like 1/10 is 0.1. 1/3 is 0.333333. It's like the value of 1/3 goes on kind of forever in base 10. Does it go on forever if you change the base though? What if it was base 3? Would 1/3 in base 3 just be 0.1? I don't know. I have theories, but I've never really tried changing a decimal number to a different base. I'm still curious about what the value of pi would look like in a different base. It's like somehow the value of pi is so intrinsic to how so many other things work. But is the number 10, like all of our math, our way of thinking is on base 10. And our calculation of pi is in base 10. But what if base 10 is not the best way to look at creation. So I am going to run some experiments on that, and hopefully you'll get to see. So, until next time, see you later.